So this is part 2 of lesson 2.5, inclined planes. So before we left off talking about the perpendicular and parallel components of gravity, and just to kind of do a brief reminder or review, the perpendicular component will always have a 90-degree angle between the surface of the inclined plane, and its job is to literally pull that object into the surface, whereas the parallel component, its job is to have that object slide down the incline. With that being said, our normal force, it changes a little bit, as you can see on this diagram. So our normal force is going to be perpendicular to the surface of the plane. And because it is perpendicular, we know that that word itself just means that it's going to make a 90-degree angle with the surface. Okay, that's all that means. And because it is going to make a 90-degree angle with that surface, it is going to be equal in magnitude but opposite in direction of FG perpendicular. Okay, so if you see this guy right here, FN, is the same length as FG perpendicular. They just point in opposite directions. So because of this relationship we have going on here, we can always say that FN equals FG perpendicular. So this is for an inclined plane. All right, because we know that if we were on a flat horizontal surface, we could say that FG is equal to the normal force. But here, like I said, we're not on a horizontal flat surface anymore. We are in an inclined plane, so therefore we do have to use a little bit of different terminology. And FG perpendicular will always be equal in magnitude to the normal force. So if you notice, they're not quite pointing up anymore. We don't have a normal force that goes. Ooh, that's kind of a bad drawing. Hold on. We don't have a normal force that goes directly up like we used to, where it was opposite the force of gravity. That's because, again, the stress is that we are on an inclined plane, and so therefore our normal force, is always going to have some sort of tilt where it makes this 90-degree angle. Okay, so FG perpendicular and the normal force, they are perpendicular to the surface of that inclined plane, and therefore it results in a 90-degree angle. So it cannot be straight up. It's going to need to be tilted, and your line should, or your vectors rather, should make that little 90-degree angle box. That's how you would check, like, hey, this looks like 90 degrees because I can draw almost a perfect box. In terms of, other forces, right? So we did have that parallel force of gravity. So with that being said, again, to review one more time, we know that the normal force and the force of gravity are equal. The force of gravity perpendicular and the normal force are equal in magnitude, so they have the same length if you were going to look at a vector diagram, and they point in the opposite direction. So, like as we mentioned before, we can say that because of that relationship, we can say it's FG perpendicular equals FN. Okay, and now we do have some other things going on. So if I'm going to push this back up, if you do notice this diagram, you'll see that FN, right, has a partner, which is FG perpendicular, and we kind of ignore FG itself because we know that FG got broken up into these two components, which we call the parallel and perpendicular components. However, notice that FG parallel does not have somebody to balance them out. Because of that, we say when there is no friction, right, the parallel force component represents the unbalanced force. And just like we know from Newton's second law, if I have an unbalanced force, we automatically know there's an acceleration happening. So because the force of gravity parallel pulls down this inclined plane or the slope, we know that unbalanced force is happening down the incline, and therefore the acceleration is also happening in that direction as well. Remember, the acceleration is always going to follow the same direction as the unbalanced force. Okay? So again, to kind of stress this, and I'm going to erase my diagrams here so that I can move this last piece. But the parallel force component of gravity will be the net force only when there is no friction. So I'm going to write that, when there is no friction. Okay, because if there was friction, then it would be a little bit of a different story, because then I'd have something to counteract FG parallel. But clearly here we don't have that. So FG parallel does represent our net force. Okay, and that makes sense. Like I said, if you have some sort of unbalanced force, that acceleration is happening in the same direction. Newton's second law tells us that. Okay, so let's move on. So kind of let's do a mid-lesson summary, so a catch-up. So what is the formula used to calculate FG per parallel, right? So FG parallel's job is to slide down. So that means if we are sliding, we are using sine. Okay, so that means FG parallel equals FG sine theta. Okay, so this is how I think of it. Sine equals slide. Okay, and then FG perpendicular, this is to pull into the surface. Right, that's the job of the force of gravity perpendicular. Because we're using sine for the one that slides down, we have only one other trigonometric function that we know. So we would say FG perpendicular equals FG cosine theta. Okay? Which force represents the net force? So again, this is a very specific condition that would arise in order for one particular force to represent this. The force that would represent the net force, if we're looking at this diagram below, would be FG parallel, but only when there is no friction, because as of right now, there's nobody else to cancel out FG parallel. So let me finish writing that down. Like I said, this guy is not counteracted by anybody else. These ones are, so we can cancel them out. We kind of just ignore FG. We don't cross it out on our own papers, but we ignore it because we know that FG was broken up into parallel and perpendicular components. Okay? So in the absence of friction, we know that there is going to be an acceleration because there's going to be some unbalanced force. So when that happens, we say that because of the absence of friction, the acceleration of the object's parallel component, which is FG parallel, it can be calculated using this formula. So this is A equals G sine theta. So what A represents is acceleration, okay? G is actually a lot more specific, and I know we don't talk about it as specific as we should in class, but G, if you recall from your reference table, is acceleration due to gravity, okay? So it's very specific to a planet's location, it's very specific per location rather. So on Earth, we know our value to be 9.81. On the moon, we're about 1.66. If we were on Mars or Jupiter or Saturn, we would definitely have a different value. So again, these really pertain on the location. And it's this acceleration that is happening because of the gravity of that planet. We know sine theta, sine is just a trigonometric function, and theta just represents the angle, okay? So, regardless, acceleration is a general term. I could be accelerating 2 meters per second in a car, but acceleration due to gravity is a very defined result. So like I said, on Earth, so I'll write, G, Earth, I'll write 9.81, and we've known that value since kinematics, okay? So to review, if there is no friction, we know that FG parallel is the only force acting on that slope point of view, right? So because that is the only force in that direction and there's nobody to balance it out, aka friction is missing, there's going to be an unbalanced force. If we have an unbalanced force, we have an acceleration happening. So that acceleration is coming from the parallel component, which we call FG parallel. And it's going to be calculated using that formula, A equals G sine theta. But that formula itself will not be on your reference table, okay? So this next part is going to sound a little crazy. We know from kinematics, we know from the first part of forces, right? On a horizontal surface, we had, oh my goodness, I'm sorry. We had at rest with the free body diagram, we had CV, and we had acceleration. Okay, so I'm going to go over them really briefly. So we would have some sort of surface. We would draw in my nice little box. FG always pulled down. FN points up. The reason why I'm emphasizing that surface is because the normal force is a contact force. It only exists when there is contact between two surfaces. So if you have an object in free fall, there is no contact between another surface. So therefore, one cannot say that there would be a normal force. So with that being said, we draw our other box. We have Fg, Fn, we have a force applied, and we have a force of friction. All of these forces are equal to each other. So if I go back to at rest, I can say that Fn equals Fg. I can say at constant velocity that Fn still equals Fg, but I can also say that the frictional force equals the force applied. Now, if I'm accelerating, it's a little bit different. As I kept saying before, if you have an acceleration, that automatically means that you have an unbalanced force. So again, Fg and Fn will still say the same magnitude and point in opposite directions, just like all the other situations. However, you will notice that one of the forces that I am drawing is going to be a different length than the other one. So notice that the force applied is greater than the force of friction, which means that that object is accelerating. And excuse me, I forgot to draw my velocity vector in. So wherever that unbalanced force is, and you can see that the force applied is a lot bigger than the force of friction, that means the acceleration is occurring where there's that bigger force. Okay, it makes sense. So notice our situation. So when we talk about it on an inclined plane, there are going to be some things that do change, and it is going to look a little uncomfortable. It's going to go against what we originally learned, but only really one situation is going to be like that. So let's review it. Okay, so let me erase this, and then we shall talk about the first scenario. Okay, so our frictional force, as we know, if it's slowing objects down, that means it is opposing the motion. Okay, and if when you hear that word oppose, think of, if I draw in the frictional force vector, that means that that object has to be moving in the opposite direction. So really, if they say, hey, the object's moving towards the right, if I were to write the frictional force in on a free body diagram, I would have to put that vector on the opposite side because it is opposing the motion of the object. Okay, so here's our first one. If the force of friction is less than the parallel component of gravity, my object is going to accelerate. And that should make sense because if one of those forces is bigger than the other one, we knew that an unbalanced force represents an acceleration, and we just talked about in the other slides that Fg parallel was in fact bigger. It resulted in some sort of acceleration down the slope. Okay? The next type of situation is if the force of friction is greater than the force of gravity parallel, our object is going to be in equilibrium, but it's going to be at rest. Okay, so, and this is going to be where it's experiencing static friction. If my object has a bigger frictional force, that is what's helping to keep it up on the inclined plane. It wants to slide down, but because I have so much friction, because that object's at rest, I have static friction, which we know is a bigger number. We'll need a bigger force to actually pull us down. Okay, so therefore, if I have a bigger frictional force, that's what's going to keep that object staying at rest on the inclined plane. But if my force of gravity parallel is bigger, it's going to result in the object sliding down the plane, which results in an acceleration. Okay, this last one, if the force of friction and the force of gravity parallel are equal to each other, my object is moving at a constant velocity. Okay, so that should sound pretty familiar to us. If it's moving, the type of friction that it experiences is known as kinetic friction, because we know that that word kinetic refers to objects in motion, whereas static is for stationary objects or objects that are solely at rest. Okay, so if we went through these rules, right? The force of friction is less than the force of gravity parallel, right? The object accelerates. That makes sense compared to what we learned with horizontal surfaces. If I have a force that's bigger than another force, yes, that's called an acceleration. An unbalanced force results in an acceleration. However, let's skip to the third one where it says the force of friction equals the force of gravity parallel. Okay, we know when two things are equal to each other, we can either say that they're at rest or they're at constant velocity. In this case, we say it's a constant velocity and then it's experiencing kinetic friction. All right, yeah, that sounds pretty much like what we used to learn back in the day. And then this last one, if the force of friction is greater than the force of gravity parallel, then the object is in equilibrium. So it's at rest. That is the one that probably sounds like we are kind of changing the rules a little bit, and it's absolutely correct. It doesn't follow that criteria that we set forth for flat horizontal surfaces. I have a frictional force that is way bigger than the force of gravity parallel, but that is very unique because I have an inclined plane. The object automatically wants to start sliding down the inclined plane. So I need a lot more friction to help keep that object staying at the top rather than it to slide down. So therefore, it makes sense that, hey, I need a bigger force of friction than my force of gravity parallel, because that force of gravity parallel is always going to exist. It's always going to make objects slide down the ramp. That's its job. However, as I've been saying, if my force of friction is greater than that value, then it will remain at the top. It will not start to slide down, okay? But if those two values are equal to each other, then we know it's sliding down at a constant velocity, okay? So out of these three new rules here, only the one in the middle sounds like the odd one out, but the other two, for the most part, they correspond to what we've learned with flat horizontal surfaces. But if you think about the second one, you're like, you know what, that actually makes sense. I want to stay at rest. I don't want to be moving, but I know that parallel component of gravity wants to pull me down. However, if I have more frictional force, I am not going to be moving. Okay? Before we end this little session, I just wanted to show the free body diagram. So as you can tell here, and I know it might be a little odd, but these guys are equal and opposite in magnitude. I know maybe this one needs to be a little bit longer, but these guys are also equal and opposite in magnitude. So now we can say that Fn equals Fg perpendicular, but we can also say Ff equals Fg parallel. And those are the two important relationships that we are going to use throughout this particular topic to solve questions.